Imagine you have 5 servers running your database. They're humming along, handling thousands of requests per second. One of them, server 1, is the leader. Every write goes through it first. Now picture this. Right in the middle of processing a critical write, server 1 crashes, just gone. No warning, no graceful shutdown. The connection drops and the other 4 servers are left staring at each other. Who takes over? How do the remaining servers agree on a new leader without losing that write, without conflicting with each other, and without any human intervention? This is the problem of distributed consensus, and the algorithm that solved it in the most elegant, understandable way is called Raft. The simplest way to run a service is with a single server. One machine, one source of truth, but if that machine goes down, everything stops. That's a single point of failure. So the obvious fix is replication. You run the same service on multiple servers. If one crashes, the others keep going. Problem solved, right? Not quite. Replication introduces a much harder problem. If 2 clients send conflicting writes to different servers at the same time, which write wins? If a server misses a message, how does it catch up? If the network is slow, how do you prevent servers from diverging? You need all the servers to agree on the same sequence of operations, in the same order, even when machines crash and messages get delayed. That's consensus. And for decades, it was considered one of the hardest problems in computer science. Until Raft made it simple. In 2014, Diego Ongaro and John Ousterhout published the Raft consensus algorithm. Their goal wasn't just to solve consensus, it was to make consensus understandable. Before Raft, the dominant algorithm was Paxos, and Paxos was notoriously difficult to understand, even for experts. Raft took a different approach. Instead of solving consensus as one monolithic problem, it breaks it into 3 clean subproblems. First, leader election. How do the servers choose who's in charge? Second, log replication. Once there's a leader, how does it keep all servers in sync? And third, safety. What guarantees prevent the system from losing data? Each subproblem has an elegant solution, and together they give you a complete consensus algorithm. Let's start with the foundation. In Raft, every server is in exactly one of 3 states at any given time. The first state is follower. This is the default. When a server starts up, it's a follower. Followers are passive. They don't issue requests on their own. They simply respond to messages from leaders and candidates. The second state is candidate. A follower becomes a candidate when it hasn't heard from a leader for a while. This is called an election timeout. The candidate then starts an election to try to become the new leader. The third state is leader. If a candidate receives votes from a majority of the cluster, it becomes the leader. The leader handles all client requests and sends heartbeat messages to maintain its authority. There's one more critical concept. Time in Raft is divided into terms. Each term begins with an election. Terms act as a logical clock. If a server ever discovers that its term is out of date, it immediately steps down to follower. This prevents stale leaders from causing problems. Let's walk through an actual leader election, step by step. We have 5 servers, S1 through S5, all starting as followers in term 1. Each server has an election timeout, a random timer that counts down. When it hits 0, that server starts an election. Server 3's timer fires first. It transitions from follower to candidate, increments its term to 2, and votes for itself. That's 1 vote out of 5. Now S3 sends a request vote message to every other server. S1, S2, and S4 receive the request. They check, is this term higher than mine? Have I already voted in this term? Since the answer is yes and no respectively, they each grant their vote to S3. S5 is slow and hasn't responded yet, but that doesn't matter. S3 now has 4 votes, which is a majority of 5. S3 becomes the leader of term 2. The first thing the new leader does is send heartbeat messages to all followers. These heartbeats serve 2 purposes. They assert the leader's authority, and they reset each follower's election timeout, preventing unnecessary elections. As long as the leader keeps sending heartbeats, the cluster stays stable. But what happens if 2 servers start an election at the same time? Say S2 and S4 both time out simultaneously. They both become candidates, both increment to term 3, and both vote for themselves. S2 sends vote requests and gets a vote from S1. S4 sends vote requests and gets a vote from S3. That's 2 votes each out of 5 servers. Neither candidate has a majority. The election fails. This is called a split vote. If this happened every time, the cluster would never elect a leader. So how does Raft prevent it? The answer is beautifully simple: randomized election timeouts. Each server picks a random timeout between, say, 150 and 300 milliseconds. Because the timeouts are different, one server will almost always time out first, giving it a head start to collect votes before anyone else even starts campaigning. In practice, split votes are rare. And when they do happen, the randomized timeout resolves the deadlock within a few hundred milliseconds. Now that we have a leader, let's see how it keeps the cluster in sync. This is log replication. When a client sends a write request, say set x equals 5, it goes to the leader. The leader appends this command to its own log as a new entry, tagged with the current term number. Next, the leader sends an append entries message to every follower, containing the new log entry. Each follower receives the message, appends the entry to its own log, and sends back an acknowledgement. Here's the key rule. The leader waits until a majority of servers have acknowledged the entry. In a 5-node cluster, that means at least 3 servers must have the entry, including the leader itself. Once the leader has majority confirmation, it marks the entry as committed. Committed means this entry is durable. It will never be lost, even if servers crash. The leader then applies the command to its state machine and responds to the client. On the next heartbeat, the leader tells followers which entries are now committed, so they can apply those entries to their own state machines too. Now for the hardest test. What happens when the network itself splits in two? Imagine our 5 servers get divided by a network partition. S1, S2, and S3 are on one side. S4 and S5 are on the other. S3 is currently the leader. On the majority side, S3 can still reach S1 and S2. That's 3 servers, a majority. So S3 continues to accept writes and commit entries normally. Everything works fine on this side. But on the minority side, S4 and S5 stop receiving heartbeats. Their election timeouts fire. S4 becomes a candidate and starts a new term. But S4 can only reach one other server, S5. 2 votes out of 5 is not a majority. So S4 cannot become leader. It stays stuck as a candidate. This is exactly the right behavior. The minority partition cannot make progress, which prevents conflicting rights. When the network heals and the partition resolves, S4 discovers that S3 has a higher term with more committed entries. S4 immediately steps down to follower and synchronizes its log with S3. The cluster is whole again, and no data was lost. Let's talk about the guarantee that holds everything together. Once an entry is committed, it can never be lost. Why is this true? For an entry to be committed, it must be stored on a majority of servers. Let's say 3 out of 5. Now, for a new leader to be elected, it also needs votes from a majority, at least 3 servers. Here's the crucial insight. Any 2 majorities in a 5-node cluster must overlap by at least 1 server. That overlapping server has the committed entry and will not vote for any candidate whose log is less up to date. This is called the election restriction. A candidate can only win an election if its log is at least as up to date as any other server in the majority that voted for it. So every future leader is guaranteed to have every previously committed entry. There's no way to elect a leader that's missing data. This single property is what makes Raft safe. It's the reason you can trust systems built on Raft with your most critical data. Raft isn't just an academic algorithm. It's running in production, right now, at massive scale. Etcetera, the distributed key-value store that powers Kubernetes, uses Raft at its core. Every time you deploy a container, scale a service, or update a config map, Raft is working behind the scenes to keep your cluster consistent. CockroachDB uses Raft to replicate data across nodes in a distributed SQL database. Consul by HashiCorp uses it for service discovery and configuration. TKV, the storage engine behind TDB, relies on Raft for distributed transactions. These systems handle millions of operations per second, across data centers, across continents, and they all trust Raft to keep their data safe. So the next time a server crashes in your cluster and nothing breaks, remember, it's probably Raft quietly electing a new leader, replicating the logs, and keeping your data consistent. That's the beauty of consensus.